The second skill that we need to learn from calculus is something called integration, or sometimes it's referred to taking an integral or integrating. So this is the opposite of differentiation or taking a derivative. The derivative takes us from something like a position function to a velocity, or from a velocity to an acceleration. And what integration does is the opposite. If we know a function of velocity, it can transform that function into a function of position instead. Or if we know acceleration, it can transform it to velocity. It also has a connection to graphs, which we'll go through in just a second, but just real quickly, if you have a velocity graph, you can look at the area, and that will tell you the x, specifically the delta x, the change in position. All right, so let's take a look at a little bit more what this means. So we have seen this before. We did this in our first year physics course, where we looked at displacement from a velocity graph. What we were actually doing is a simple form of this process of integration. We just only looked at situations where we could do it geometrically instead of having to use this calculus idea. But recall that we broke a shape into smaller shapes, and we added up, or we summed up, the areas for each of those sections. A rectangle was just velocity times time, or maybe we had a trapezoid or a triangle that we had to deal with. But to find delta x, we added up, or we summed the areas. If we have something that's more complex, like a curve, like this picture is showing, then we can't just figure out the shapes very easily. And again, this is explained in much more detail in a full class of calculus. You are getting the quick version of it for our class. But you have to do this in a much smoother way. You can't just break things into these choppy shapes and so forth. And so our sigma is smoothed out. That's how I always thought of it. And so this symbol is a smoothed out S. It is a smoothed out adding up of our basic areas. And as you see here, our basic areas were a velocity times a time. And so that's what we see in this representation too. This is the notation that is used to represent the idea of adding up areas to determine what the displacement is. But we're not going to actually be adding up areas. We are going to learn a process of taking a function of velocity and transforming it into a function of position. One little thing that's going to be a bit different from the derivative. When you take a derivative, there is always a single answer. There is just one possibility as to how the velocity function is formed from the position function. What the slope of the line is. There's only one possible answer. But in this case, if you're trying to figure out what the position function is from a velocity graph, there's actually a number of possibilities. So kind of thinking backwards, if we started with this, if we knew that the velocity was consistently changing with a constant acceleration, can you predict exactly what the object was doing? Well, you can predict the general shape. You can predict how the motion is changing, but what you can't tell is where the object started. That information is not contained in a velocity graph. So there's always sort of this unknown value. It's a constant number for a certain problem, but this unknown initial position that has to be defined elsewhere. You have to be told what that is somewhere else. And so if you're actually trying to find the position, not just delta x, but the actual position function, you do this process that I'm going to explain in a second, this integration, and then you have to add the initial position to it to really define the complete function. Okay, so just like with the derivative, there is a general rule that's on our formula sheet, and it's sort of written here. Something I didn't mention with the derivatives is that the general format uses x's like kind of like a math class would, where in physics we tend to use time, especially at this point in physics. So that can get a little bit confusing. We'll go through that in class though. But let's again look at some examples. So if my velocity function looks something like this, let's say it was 3t squared. I'm going to keep this kind of simple right now. 3t squared. If I wanted to find the displacement, if I wanted to find out how far the object moved, what I would do is I would integrate my velocity function with respect to time. What that means is that this little dt, that defines that time is the horizontal axis. That becomes important later on in our class. But what we're really doing is we are integrating 3t squared, again, with respect to time. This is just a formal notation that has to be included. Now, how do we do this? Well, again, I'm just going to show you the answer and let you kind of see if you can see how it works. So this one turns out to be just t cubed. Let me take a look at another example. If my velocity were 10t plus 6t squared, then to find delta x, to find my displacement, I would integrate my velocity with respect to time, meaning I would integrate 10t plus 6t squared with t as my variable. All right, and again, I'm just going to show you the answer, and we'll see if we can sort of see the pattern. The answer here is 5t squared plus 2t cubed. All right, let's see if we can follow what this pattern was. So over here, there was a 3 and a 2. I'm going to focus on the 2 first. The exponent was 2 in my original function. It became a 3 in the new function. So it increased. And then I had this 3 in front, but it dropped out. It's almost like I divided the function by 3 and got rid of it. That's how I want you to think about it. This next one, okay, I started with 10t. Remember, that's really 10t to the 1. So my exponent of 1 transformed into an exponent of 2. It increased by 1. And then it's like my 10 was divided by 2. That same number, 2. 6t squared. My squared went up by 1. It increased to 3. And then my 6, it's like it was divided by 3. So that's what the rule is. The idea is that when you integrate, when you follow this particular rule of calculus, whatever your exponent is in the original function, it goes up by 1 in the new function. And then remember, with derivatives, we ended up multiplying by an exponent. In this case, what we end up doing is dividing by the new exponent, dividing by that the 3 or the 2, that kind of thing. So we will go through some more examples in class. We'll also talk a little bit about what happens if you actually need just the function of position and not delta x. But those are all kind of more complex thoughts.